Section 4.8 in our Algebra 2 book is called complex numbers. So we're finally now going to get into an idea that we've been avoiding carefully the entire chapter, and that's this concept right here of imaginary numbers. And I won't dwell on this too long, but I do like to draw this parallel question here, everybody. Does a kindergarten kid understand the concept of positive numbers? It's actually an interesting question. On the one hand, yes, because all the numbers that a kindergartner knows, 1, 2, 3, 4, 5, whatever, are in fact positive numbers. But they don't really know that they're dealing with positive numbers because they don't understand anything that's not positive. You don't really understand positive numbers until you begin to understand negative numbers. So, with that regard right here, do we know what imaginary numbers are? Not really yet. But what's important here is that imaginary numbers are, in fact, let me just write this right here nice and quickly, not real numbers. So, much like I asked just a second ago, does a kindergartner understand what a positive number is? Does an Algebra 2 student understand what a real number is? Well, yes and no. Every single number that you guys have learned up until right now in your life has been a real number. Because if I were to come up with a number line here, guys, and say, okay, here's 0, and here's positive 1, and positive 2, and then negative 1, and negative 2, every number in the world, you guys could tell me where on that number line it exists. Okay, this is 2. This is negative 1. Even a weird number like pi is somewhere between 3 and 4. So I could guess, okay, that pi would probably be right about there. Or even a weird number like the square root of 5 would be on there as well. But now we start talking about imaginary numbers. And quite simply, imaginary numbers are not real. What does that mean? Well, here's the more formal definition. A number that cannot be graphed on the real number line. That doesn't really answer the question. Let's dive into it, guys, and you'll get the hang of this pretty quickly. There is really only one imaginary number that you need to know, and that's this one right here, which we call I. And the numerical definition of the number I is something that isn't going to make a whole lot of sense. I is the square root of negative 1. Now, I want you to think about that for a second. For example, okay, if I asked you what's the square root of 49, you guys would tell me the answer is 7, because 7 times itself equals 49. Although by that rationale, negative 7 works as well, but let's not focus on that right now. 49 has a real square root, it's 7. But if I ask you now, okay, what's the square root of negative 1? What number times itself equals negative 1? Well, the answer can't be positive because a positive number times itself, in fact, let's write this out, a positive number times another positive would equal a positive number, not a negative. A negative number times itself would equal a positive number as well. So this answer can't be negative. And the third possibility would be 0. 0 times itself equals 0. Every real number is either positive or negative or 0. And no matter which of those three cases you look at, squaring one of those numbers never gets you a negative result. So, the square root of negative 1 kind of defies logical explanation. It's tempting to say there is no number out there multiplied by itself that equals negative 1, and what you're really saying is there is no real number out there times itself that equals negative 1. But there is an imaginary number. I is how we define it, and it's the square root of negative 1. Now that, you guys, is the only, let's do that. That is the only imaginary number that you guys really need to know. Everything else we're going to do in that list is a variation off this same thing. Here we go, I squared. Let me rewrite this original statement over here. I is equal to the square root of negative 1. And if I now want to ask you guys, what's the value of I squared? We're going to square the left side and square the right side of this equation. So you get I squared is equal to, and now on the right, the square and the square root cancel each other out, and I squared is equal to negative 1. Okay, now I said this is the only real imaginary number you need to know, but this right here, the value of I squared equaling -1, that is equally important, if not more important, for you guys to know. So I would put a box around these two statements right here, and I would make sure that we understand all of that. The rest of this, you guys, is all just a variation on that idea. Like, for example, if I now want to know the value of I cubed, I'm going to take this equation right here and multiply both sides by I times I squared is equal to I cubed. And my right side, -1 times I, is -I. So I cubed is -I. And there we go. That wasn't that bad. All right, I can do that same trick again now to get I to the 4th. I can take my I cubed equation right here and multiply both sides by I again. I times I cubed is going to get us I to the 4th. And now on the right, okay, I times I is I squared. And right here on this line, maybe that line right there, I squared is equal to -1. But there's still this negative out in front, guys. So this is the opposite of -1, which equals +1. So I to the 4th is 1. Okay, some weird concepts right here, everybody, but everything we have now is a variation on that. The weird thing that happens next, I'm going to keep going with this list just a little bit farther, is you're going to start to see a cyclical pattern repeating itself here. If I wanted I to the 5th, okay, let me just keep doing the same thing I'm doing. I'm going to take my previous equation now of I to the 4th and multiply both sides by I again. I times I to the 4th is I to the 5th. And here we go. 1 times I is just I. So I to the 5th is I. Okay, gotcha. You'll notice that is the same, everybody, as I to the 1st power right there. Let's do it again now. For the next one right here, we'll take this line, and to get I to the 6th, let's multiply by I again on both sides. I times I to the 5th is I to the 6th, and then I times I is I squared. But wait a minute, back to this line right here, I squared is equal to -1. So there you go. I to the 6th is -1, which is the same value here as I squared. This thing just starts to repeat itself over and over and over again. So let me show you how you handle something harder like I to the 19th without going through this over and over again. Basically, guys, when the powers increase by 4, you end up with the same result. Did you notice that? I squared was -1, so was I to the 6th. I to the 1st power is just that square root of -1, same thing for I to the 5th. So I to the 19th, everybody, is the same thing as I to the, let's subtract 4 from that power. 19 minus 4 is 15, which would be the, I don't know I to the 15th either. So let's subtract 4 again. It would be the same as I to the 11th, which would be the same as I to the 11 minus 4 is 7. I don't know that one. So let's subtract 4 again. It's the same as I to the 3rd. And right here, I to the 3rd is -I. So we just have to keep subtracting 4 over and over and over again, although that can get a little bit tedious. So let me show you maybe a quicker way to do that. I to the 26th. Here's the way you do it, guys. You take your 26, you divide it by 4, and let's do this division the way you learn to do it in 4th grade. 4 goes into 26 6 times. That's not really important, but here's what is, with a remainder of, 4 times 6 is 24, 26 minus 24 is 2. Your remainder of 2 tells you that this is equal to I to the 2nd power. Look at the difference, guys, between 26 and 2. That's a difference of 24, which is a multiple of 4. And the value of I squared, right up here again, is equal to -1. So you don't really need that as part of your answer here, but there you go. I to, ooh, that was ugly, sorry. I No, why is that not moving here? I give up. All right. Nope, forget it. Leave it there. I to the 26th is -1. And that last one, let's try that trick again. Whew, I to the 501st power. We would do 501 divided by 4. And if you check that in your calculator, I'm pretty sure that goes in 125 times. But the remainder then, 125 times 4 is 500. That's a remainder of 1. So this is equal to I to the first power, which is just plain old I. Okay, that was lots of fun, wasn't it, guys? I'm sure. As long as you guys can memorize these two things up here in the box, you're probably good to go. Okay, all right. So, that did not display when I tried to print this here. What was I doing here? Oh, I remember what this was now. Okay, guys, so let's just ignore. Can I just get rid of that and say go away? No, it's stuck there. I'll just write over it. What I was asking you here, guys, was how about the square root of a negative number, like the square root of -49? Let's talk about that. And the way we're going to do this, everybody, is with the process we were using earlier in this chapter of simplifying radicals. We're going to break that 49 up into -1 multiplied by 49. Hopefully everybody understands why we can do that. And now, the property for simplifying radicals says that we can split this up into the square root of -1 multiplied by the square root of 49. And both of these can be simplified, you guys, although I'm going to change the order. The square root of 49 is 7. And the square root of -1, wait a minute, let's go back right here. The square root of -1 is I. So I'm going to put an I at the end of that, and that's our answer there, guys. The square root of -49 is 7I. Now, have you learned something there? The square root of a negative number isn't that hard. You take the square root of the positive version of that number, that's where the 7 came from, and if there was a negative, you just stick an I at the end of it, and it isn't all that bad. So let's do one that's a little bit different. What if I gave you guys, I don't know, how about the square root of, I don't remember what this problem was, but I'm going to make it negative, and then we're going to go with, how about the opposite of the square root of 80? Now this one's a little bit tougher because 80 is not a perfect square, but we're still going to split this up in a similar way. -1 times, and all right everybody, can you look at your list of perfect squares from back in section 4.6, I believe, and come up with a perfect square that divides evenly into 80? You cut 80 in half and come up with 40. The first perfect square less than 40 is 36. But 80 doesn't divide evenly by 36. It doesn't divide evenly by 25, but it does divide evenly by 16. And it's 16 times 5. So now we will break that up into the square root of -1 times the square root of 16 times the square root of 5. That one and that one can be evaluated here. So what happens? I'm going to go a little out of order. The square root of 16 is 4. The square root of -1 is I, and you can't do anything with the square root of 5, so it just tags along at the end. So the square root of -80 simplifies into 4I times the square root of 5. So it's still the same concept of simplifying radicals, but now we break out a -1 and we have an I involved in our answer. All right, I lost the text here. All right, here's some of the things you're going to be asked to do on homework here, guys. For starters, simplifying each expression. This one involves some addition and subtraction of what we call complex numbers, which have both a real component, like that, but also an imaginary component with an I. And let me give you guys some good advice. So here goes. Listen carefully. I is not a variable. However, you can treat I just like a variable with all the rules that you guys have learned for that in the past. And the reason why is because all the rules that you guys have learned for variables aren't really just rules for variables. They're rules for all numbers. So let me say it again. I's not a variable, but you can treat it like one. So the first thing I would do here is distribute that negative there, and then this set of parentheses isn't really serving a purpose because there's a plus sign out in front. So I would rewrite this as 6, and then the minus negative 2 is a plus 2, and minus positive 9i is minus 9i. And then we've got a plus negative 8, so that's a minus 8, and a plus 4i is going to go right there. And let me say it again, I is not a variable, but you can treat it like one. So let's add together our real numbers first. 6 plus 2 makes 8, and 8 minus 8 is 0. They all cancel each other out. And then we have a negative 9i plus 4i. And treating I like a variable, that would give us negative 5i. And guys, there is nothing else you can do with that problem. That's our answer here for adding and subtracting with these complex numbers. Our answer ended up purely imaginary because all of the real numbers dropped themselves out. Okay, let's try another one. Here we have two complex numbers being multiplied together. So hopefully you guys remember binomial times binomial is when we're going to do FOIL. First, outer, inner, last. Now there's one little trick you have to remember at the end of this problem when you're doing FOIL with complex or imaginary numbers, but we don't have to worry about that yet. Let me say it again. I is not a variable, but you can treat it like one. So here we go. First product, 7 times 4 is going to give us 28. Outer product, 7 times 2i is a plus 14i. Inner product right here, negative 3i times 4 is a minus 12i. And then the last product, here times here. Negative 3 times positive 2 is negative 6. I times I is I squared. Now, what you guys are used to with FOIL is that the two terms in the middle are alike and can be combined, and that happens here as well. 28, and then we end up with a plus 2i in the middle from a plus 14 minus 12. But here's something you're not used to. You are never allowed to leave an I squared in your final answer. Why? Because let's go back to the first slide. I squared can be simplified into negative 1. So this is now minus 6, but the I squared becomes negative 1, and that gets multiplied by the 6 there. So what do we have? 28 plus 2i, and then a plus 6 now. That was negative 6 times negative 1, and that gives us two real numbers here that can be combined. 28 plus 6 is 34, and a plus 2i. And there's nothing else we can do to simplify that complex number there, so that's our answer here, 34 plus 2i. So that's what it looks like to FOIL or to multiply two complex numbers. Okay, this is a very similar problem to the one that we just did. The only difference here being that the two complex numbers we're being asked to multiply right here aren't just random. These two have something in common. They have identical first terms, 9 and 9, but opposite second terms. Those are called conjugate. I've used this word a few times here. Conjugate binomials, although actually in this case they're called complex conjugates because they're complex numbers. And the same thing that always happens when you multiply or FOIL two conjugates is going to happen here. Let's check it out. First product, 9 times 9 gives us 81. The outer product right here, 9 times 4i, is a plus 36i. The inner product, negative 4i times 9, is a minus 36i. And then the last product, this number times this number, negative 4 times positive 4 is a negative 16, and I times I is I squared. Let me say it again. I is not a variable, but you can treat it like a variable. Now, what I'm hoping you guys remembered, anytime you do FOIL with conjugate binomials, the outer and the inner products are always going to be exact opposites of one another, which means they cancel each other out. gone. So what are we left with here now, guys? 81 and then minus 16. But remember, you can't leave an I squared in your answer. I squared becomes negative 1. So now I've got to do an 81, and then this is minus 16 times negative 1. That becomes a plus 16. And 81 plus 16 is 97. Now, the big difference between the problem we did previously, this one right here, and the problem we just did here is that in example B, we FOILed out two complex numbers and ended up with a complex number because it has an imaginary component. But in example C, when we FOILed two conjugate binomials, the imaginary part of the number right here dropped out completely, and we ended up with an answer that was completely real. There was no imaginary component to it because all of the i's are gone. And that concept right there, that foiling two conjugate binomials is going to get you a purely real number, becomes pretty important when we start doing division by complex numbers. So the rule we're going to try to follow here, guys, is that we're not allowed to keep an I in the denominator. We have to find a way to get rid of it, and here's how we do it. We're going to take this fraction and multiply it now by the conjugate of its denominator. 5 plus 4i has a conjugate of 5, same first term, but now minus 4i. We multiply that on the bottom, and we have to multiply the exact same thing on the top. Why? Because 5 minus 4i over 5 minus 4i, any number divided by itself, is 1. So all we're really doing is multiplying that blue fraction times 1, which doesn't change the value of the fraction. Not the value, but it will change the form. Okay, so what does it look like? Up in the numerator, guys, we have a monomial, 7, times a binomial, 5 minus 4i. That is when we use the distributive property. 7 times 5 is 35. And 7 times a minus 4i minus 28i. That wasn't that bad. The denominator is going to be harder. The denominator is a binomial times its conjugate binomial. We have to do FOIL. So just looking in the denominator, guys, the first product, 5 times 5, 25. The outer product there, 5 times a minus 4i, negative 20i. The inner product right there is a plus 20i. And then the last product, this times this, positive 4 times negative 4 is negative 16. I times I is I squared. Okay, what can we do to clean this up? In the numerator, nothing. 35 minus 28i. They're not like terms. Nothing can be combined. But down in the denominator, two cool things happen. Just like before, negative 20i, positive 20i, they're opposites. They cancel each other out. So now we've got a 25, and then it's minus 16, but the I squared needs to be replaced yet again by a negative 1. And I'm going to work sideways here, guys, because I'm running out of room. So we've now got a 35 minus a 28i, all over. That is now a 25, and then plus 16. Okay, so we're at a 35 minus a 28i, all over, and 25 plus 16 is 41. In some cases, there might be one more step you can take. You would need to look at this number here, and this number in the denominator. And if all three of those numbers have a common factor that can be divided out, that's what you would have to do here. Luckily for us, there's no number that divides evenly into 35 and 28 and 41. And so this answer that we have right here is our final answer with a purely real denominator. 35 minus 28i all over 41. Okay, so that's how you handle a division problem with i's in there. And I'm going to give you one more here that's not going to be fun, but this type of problem shows up here too. Sometimes you end up with radicals involved in there too. Now, same basic process, guys. We're going to multiply both the top and the bottom by the conjugate of your denominator. So here we go. The denominator was 3 minus I root 3. Its conjugate is going to be 3 plus I root 3. And you do the exact same thing on the top that you did on the bottom. They both get multiplied by 3 plus I root 3. Okay, so where does that get us? We've got some foiling to do on both the top and the bottom. Up on the top, 5 times 3 is going to get us a 15. The outer product is going to be a plus 5i times the square root of 3. The inner product, this one times this one, is going to be a plus 3i times the square root of 12. And then the last product, this times this, positive times positive is a plus. I times I is going to be I squared. And root 12 times root 3 is the square root of 36. Oh, that's fortuitous. You'll find out why in just a second. Down on the bottom, let's do FOIL all over again. 3 times 3 is going to be a 9. Outer product is a plus 3i root 3. Inner product is a minus 3i root 3. And then at the end, this times this. Negative times positive would be minus. I times I would be I squared. And root 3 times root 3, let me be consistent here, is the square root of 9. Something cool is going to happen there. Now, the only nice thing that I see right here is that this term and this term are opposites and will cancel each other out. Okay, so that's progress. I'm also going to save a little bit of time here, guys. This I squared right here becomes negative 1. And in fact, so does this I squared here as well. So let's see what that does for us. We've got a 15 plus, oh boy, I made this harder than I needed to, but okay, that 12 right there can be simplified into 4 times 3, and the 4 we can take the square root of and bring it out in front. So that's a 5i root 3 plus, the square root of that 4 is 2, times 3i is 6i, times the square root of 3. And then at the end here, the I squared became a negative 1, the square root of 36 is 6. So that's going to be a minus 6 at the end of that line. And down in the denominator, we've got a 9. These terms we said canceled out. And then what's going on here, guys? Now this was a minus I squared. That is minus negative 1. So that becomes a plus 1 times the square root of 9, which is 3. Whew, there's a lot going on in this problem right here. Okay, and let's see what we can do next here, everybody. Let me draw a little line there, and here we go. Up in the numerator, the first term and the last term can be combined. 15 minus 6 is 9. Let's combine these like terms now to get a plus 11i times the square root of 3 all over the 9 times 3 on the bottom, which is 12. And once more, we would need to look here and here and here. And if there's a common denominator, or a common factor, I should say, we need to divide that out. But again, there isn't one. That is our final answer to this example. And that, you guys, is a pretty darn tough problem there. There was a lot going on there, and that's where we ended up with. All right, there's 3 more examples I want to do with you that show you how to use imaginary numbers to solve goofy quadratic equations, but I'm going to cut this video off and I'll make a second one for that.